So here we'll continue with our lesson on fundamental quantities and their dimension, right? So dimension, like I said before, simply means expression of physical quantities in terms of fundamental quantities, right? And these are the basic fundamental quantities that we have. Fundamental quantities, like I've mentioned before, they are basic quantities. They are those basic quantities or elementary quantities that cannot be defined in terms of other quantities, in terms of other physical quantities, and they form the foundation for expressing all other physical quantities, right? So the seven major fundamental quantities that we have in physics, they are mass, length, time, electric current, temperature, amount of substance, and luminous intensity. The dimension for mass is m, the dimension for length is l, the dimension for time is t, the dimension for electric current is I, dimension for temperature is theta, dimension for amount of substance is n, then for luminous intensity it is j, right? So it is very important that we know the derived quantities, the major derived quantities and their formulas. We have something like speed. Speed is equal to distance all over time. We have velocity as a derived quantity and it is equal to displacement all over time. Acceleration is equal to velocity over time. Force is equal to mass times acceleration. Work done is equal to force times distance. Power is equal to work done all over time. Pressure is equal to force all over area. Density is equal to mass over volume. Area is length times length. Volume is length times length times length. Momentum is mass times velocity. Impulse is equal to force times time. And then electric charge is equal to current times time. So all these derived quantities, is very important that you know the different formulas for them, right? So it's something that you've got to memorize. So having known this, let's dash to the business of the day. So what is the dimension of acceleration? What is the dimension for acceleration? So the first thing that you want to do is to put down the formula for acceleration, right? Acceleration is a derived quantity. So the formula is acceleration is equal to velocity over time, right? We've got it here that acceleration is equal to what? Velocity over time. So time is a fundamental quantity and the dimension is capital T, but velocity is a derived quantity. So what would you want to do? You want to look for the formula of what? Velocity. Because dimension is all about expression of physical quantities in terms of fundamental quantities. So whatever you're going to have here as your answer must be in fundamental quantities, right? So velocity is equal to displacement all over time, right? So your displacement is a fundamental quantity, time is a fundamental quantity, right? Displacement is a fundamental quantity and its length itself. Time is a fundamental quantity. So the dimension for velocity is what? L. Displacement is what? Length, right? So it is L all over what? T. So this is the dimension for what? Velocity. So if I put that here, my acceleration will be equal to, so instead of me to write velocity here, I'm going to write the dimension which is L all over T, right? So that will be L all over T times what? The T that I have here. That will give me my acceleration. So acceleration is equal to L all over T squared or L T raised to the power of what? Minus 2. When I take this power T raised to the power of 2 up, it becomes T raised to the power of minus 2. So this is my dimension for acceleration, or this is my dimension for acceleration. Both are correct, right? So let's dash to the next question that we have here. What is the dimension of work done? What is the dimension of work done? So the first thing that you want to do is to write out the formula for work done. So work done W is equal to force times distance, right? Work done is equal to force times distance. So it is very important that you know these formulas for these different derived quantities. It will help you to be able to write out their dimension. So work done is equal to force times distance. Then distance is a fundamental quantity. It is represented as L. Distance, length, displacement, they are all the same, right? They are represented by L. So my work done will be equal to force times distance, whose dimension is what? L. Force is a derived quantity. For that reason, I would want to look for the formula for force, or the dimension for force rather. So force is equal to mass times acceleration. Mass times acceleration. So mass is a fundamental quantity, right? Acceleration is a derived quantity. So I would want to look for the formula or for the dimension of acceleration. So acceleration is equal to what? Velocity over time. Time is a fundamental quantity, but velocity is a derived quantity, right? So I would want to look for the dimension of velocity. So velocity is equal to what? Displacement over time. Displacement is a fundamental quantity. Time is a fundamental quantity. So what is the dimension for displacement? It is L. Dimension for time is what? T, right? So this is my dimension for velocity. So if this is my dimension for velocity, I can put it into acceleration. Acceleration is velocity all over time, right? So my velocity, instead of me to write velocity here, I will write the dimension of velocity, which is L all over T times the T that I have there before, times T. That will give me my acceleration, right? So acceleration is equal to L T raised to the power of what? Minus 2. This is my dimension for acceleration. So I can put that here. Instead of me to write acceleration here, I will write Lt raised to the power of what? Minus 2. So my force, which is mass times acceleration, will now be equal to m. The dimension for mass is m, right? The dimension for acceleration is Lt raised to the power of what? Minus 2. So this is my dimension for force. So I can simply put that here, that my work done is equal to force times length, right? So the dimension for force is ml t raised to the power of 1 minus 2 times the L that I have here. That is my dimension for work done. So work done will be equal to L times this L will give me L squared, right? So that will be ml squared t raised to the power of what? Minus 2. L times this L will give you L squared. So that's how we got ml squared t raised to the power of minus 2. This is my answer for the dimension of what? Work done. So this is the dimension for the work done. Just have it in mind that whenever you are looking for dimension, you are expressing the physical quantities in terms of fundamental quantities. So whatever you're going to have here as your answer must be in fundamental quantities, right? So let's look at the next question to buttress on this more. What is the dimension of power? What is the dimension of power? So the first thing that you want to do is to write out the formula for power. So power is equal to work done over time, right? So we've already looked for the formula for work done, the dimension for work done, and work done is equal to ml squared t raised to the power of minus 2, right? So that will be equal to ml squared t raised to the power of minus 2, that's the dimension for work done, over t. So that's the dimension for power now, right? So this will now be equal to ml squared t raised to the power of minus 2. When this t comes up, it becomes what? Minus 1. It becomes t raised to the power of what? Minus 1. So T raised to the power of minus 2 times t raised to the power of minus 1, according to indices, will give you ml squared t raised to the power of minus 2 plus what? Minus 1, right? So plus times minus will give you what? It will give you minus. So this will be ml squared t raised to the power of minus 2 minus 1, because plus times minus will give you what? Minus. So this will be ml squared t raised to the power of what? Minus 3. This is the dimension for power. It's very simple and straightforward. What is the dimension of density? What is the dimension for density? So density, first thing that we want to do is to write out the formula, right? Density is equal to what? Mass over volume. Mass is a fundamental quantity, and so the dimension is m. Volume is a derived quantity. It's a derived quantity. So we would want to look for the formula for volume, right? So this is mass all over what? Volume. Mass all over volume. So volume as a derived quantity, volume is equal to length times length times length, right? So the dimension for volume will be equal to what? L squared, L cube. L times L times L, that will give you L raised to the power of 3, L cube, right? So the dimension for mass is what? The dimension for mass is m. Dimension for volume is what? L cube. So the dimension for density will be equal to m L raised to the power of what? Minus 3. When this L raised to the power of minus 3 comes up, when this L raised to the power of 3 comes up, it becomes L raised to the power of minus 3. So density, which is represented as rho, is equal to m L raised to the power of what? Minus 3. This is my formula. This is my dimension for density, right? So let's look at the last question that we have here. What is the dimension of momentum? Momentum. So the first thing I want to do is to write the formula for momentum, right? So momentum is equal to what? It's equal to mass times velocity. Momentum, this is momentum. Momentum is equal to mass times velocity, right? So mass is a fundamental quantity. So the dimension is m. Velocity is a derived quantity. So we have to look for the dimension of velocity. So velocity is equal to what? Displacement all over time. And displacement is a fundamental quantity. It is length, right? So that will be equal to L. The dimension for displacement is L, which is the same thing as length, over T. T is a fundamental quantity, time. So the dimension for velocity is V is equal to L T raised to the power of what? Minus 1. When this T comes up, it becomes L T raised to the power of minus 1. So this is the dimension for velocity. So this will be times m lt raised to the power of minus 1. So my dimension for momentum will be equal to m lt raised to the power of minus 1. This is the dimension for momentum. So it's very important that you know the formulas for the different basic derived quantities. Speed is equal to distance over time. Velocity is displacement over time. Acceleration is velocity over time. Force is mass times acceleration. Work done is force times distance. Power is work done over time. Pressure is force all over area. Density is mass over volume. Area is length times length. Volume is length times length times length. Momentum is mass times velocity. Impulse is force times time. And then electric charge is current times time. So all these are very important for you to be able to write the dimension of any of these physical quantities.